All right, welcome in Calc 3. It's Sunday, September 19th, and this is the recording that should have happened on Tuesday, the 21st, but of course I'm not available to record on that day, so I'm recording this one early, yeah? So we are covering 12.2 in this video today. We've been talking a bit about vector-valued functions and talked about limits and how they were continuous and all of the other things that we do with functions. And then we're talking a bit about today differentiation and integration of vector valued functions. I have really good news for you in this way, because to differentiate a vector, all you have to do is differentiate component wise. And to integrate a vector, all you have to do is integrate component-wise. So the actual act of differentiation and integration is completely easy. It's like two problems in one or three problems in one. You just literally, if I want to take the derivative of a vector, I differentiate the I component, the j component, the k component, and then there you have it. So conceptually, we're going to talk a bit about what those do and what they mean, but practically speaking, very easy to calculate. You just do it component wise, like so much, like so many other things we do with vectors. Yeah. So awesome. Let's get started with some details now. So 12.2, it's all about differentiation and integration of vectors, vector valued functions. Okay, so we do have the definition of differentiation, and thankfully, we don't have to use this definition for actual calculation purposes, but it is instructive to think about it conceptually, just as it was in Calc 1. So the derivative, so if I have r, I'm going to define r prime to be the limit as delta t goes to 0 of r of t plus delta t minus r of t divided by delta t. Now, this is the same exact format as we had in Calc 1 for just a regular old function with a real number valued output, yeah? So let's talk a little bit about what this would mean, right? And I have a visual here that I can pull up on GeoGebra for this, right? Think about, right, this is r of t, so it's pointing to a certain location in space. And this is pointing in some future time, t plus some future time, right, delta t. And so these are two vectors, and I'm looking at their difference. So let's go ahead and get to GeoGebra real quick on what we got going on here. So I have a function, doesn't really matter the function is this curve like this, right? And I've graphed r of t right here. So r of t is pointing right at that location. And then r of t plus delta t is the t value plus some delta. So basically it's a head in time and it's pointing over here, right? Now visually think about what it would mean to take the difference of those two vectors. Well, you might remember that to add vectors, you connect them like you connect this tail to the head of the arrow, and then you attach the tail of the one that you're adding and go to the tail there. But we want to add the opposite, right? Because it's subtraction. So let's vision this together. We're going to start with r of t plus delta t, which is pointing out this way. Then we're going to add the opposite of r of t. Well, r of t is going to the right, so the opposite would be going to the left. So it would end me up over here somewhere. Then we, of course, pick it up and move it, and you might recall from our early work with vectors that the difference finishes this triangle, right? And so we actually have the difference of those two there, right? Oh, I feel a sneeze coming. Excuse me. So anyway, what we have here is the difference. This completes the triangle, yeah? So what I'd like to do now is see what happens when I shrink the delta. Right now, the delta is 0.9, and that doesn't mean much, but I want you to notice what happens to this difference of the two vectors, which is the numerator of the limit that we're calculating. So when I shrink delta to be smaller and smaller and smaller, notice the direction that that arrow is going in. See that? It's shrinking to nothing, isn't it? It's shrinking to nothing. But now we're going to take that delta, the difference, this vector here, and divide it by delta t, divide it by the delta. That is the denominator of the definition of the derivative that we were looking at. So I'm going to go ahead and turn that on. Now watch this, what happens. Dividing by that scale keeps the direction of the difference, but because I'm dividing by a scalar, it keeps the direction, but it also will change the magnitude. Now watch what happens as delta gets smaller and smaller and smaller. See what happens to this graph, all right? And in fact, I can't take this to 0 because it'll disappear, right? But I can get it to as close to 0 as this will allow, which is like 0.0001. See that? From this point, I think you can tell, look at this. I end up getting a derivative vector that seems to be pointing tangent to the travel curve, right? So if I imagine that this I imagine that the r is pointing to a certain location, it looks like the derivative vector can be interpreted as saying what direction you're flying in at that moment. That is super useful, and that is why the derivative of a vector is hugely helpful, right? So if you think of r of t pointing to where you're at, you can think of r prime of t pointing in the direction you're going. You see that? And that visual is right there. And so that will keep track of the direction we're going. Now, because this is going to come up so often, I'm supposed to hold off because the next section is called acceleration and velocity. Let's just go ahead and go there. R of t often represents a position, right? Where something is at. And the derivative would then be its velocity. This tells me that the velocity vector points in the direction of motion, right? If you want to know what direction you're going in 2 space or 3 space, check out your velocity vector. The velocity vector is defined in such a way as to point in the direction at which you're flying at that instant. The magnitude of the velocity vector is how fast you're going, the speed. And so that vector, that velocity vector, does a couple things. It tells you the direction you're going, and it tells you how fast you're going in that direction. What a really useful result. And so taking the derivative of a vector is easy component-wise, but conceptually it's really beautiful to look at as well. It really gives you information along this vector valued functions curve like that. Very cool. All right, let's get to some on paper examples here where we just basically practice this a little bit. So our first example. Now, thankfully, we don't have to use the limit definition in actual calculation. We already know all of our shortcuts and those sorts of things from Calc 1, and so we're good to go. So this becomes really straightforward. Suppose I have a position function, ti plus t squared plus 2j, like that. And that's my vector valued function, and let's say it represents a position, right? Then I want to calculate r prime. This really is as simple as taking each component and taking the derivative with respect to t, the parameter. So t with respect to t, that's 1. And so I just get I plus the derivative of this is 2t plus derivative of 2 is 0. So I get j. See that? So this would represent position. This would represent my velocity at time t. So position at time t, or parameter t, if you don't like time being negative, velocity at time t, or some parameter value, yeah? Awesome. And so I can say, well, hey, if the parameter value is 1, what is my position? So where am I at when t is 1? Well, I'm located at 1i plus 3, 1 squared plus 2, 3j. And what direction am I flying in at that point? That would be r prime at 1, which is I plus 2j. See that? So that would be my position and velocity at t equals 1. See what I mean? Couldn't be easier. So now you just have to de-rust a little bit. If you have struggled with taking derivatives, well, they're coming back with a vengeance, because each problem is like a 2-for-1 deal or a 3-for-1 deal, right? If I had 3 space, I would be taking the derivative of 3 components and would have to work with that then as well. Okay. All right, let's continue on. Let's look at a couple more examples here. Suppose I have a position function, r of t equaling cosine of ti plus sine of tj plus 2tk. You might remember this is the helix we were working with, I believe on Thursday. Yeah, this is a 3-dimensional, if I look above, it's a cosine sine pair, so I see circular motion, and that particle is rising as it circles. So it's a helical pattern, yeah? We want to calculate a whole bunch of things here. Let's first off calculate if this is position. Let's go ahead and calculate the first derivative, which would be velocity, of course. And so the velocity here, derivative of cosine of t is negative sine of t, I. Derivative of sine is cosine. And the derivative of 2t is 2. So this would represent the velocity. And we can go further, right? What's the second derivative of r? Well, that would be the derivative of negative sine is negative cosine. Derivative of cosine is negative sine. And the derivative of 2 is 0. You see that? And so the k component of the acceleration, right? That's what we call the second derivative when the function represents position. Notice that the k component shrinks to 0. Yeah? So the change in the direction that I'm flying, yeah? See that? It doesn't change in the k direction, right? Now I'm flying with a constant k, so this is spinning, right? That's what this is telling me. When I look at the velocity, it means I'm spinning around, and I'm climbing at sort of a constant rate as I do that. Yeah, so it's at a constant rate there, which means that there is no change in that rate. So I have a 0 acceleration in the k component. Another kind of interesting thing here is, do you see that r is this? And look at this. The I components are opposite and the j components are opposite. This tells me that the acceleration of this particle is pointing towards the center of the helix. All right, that helix is going around, and the acceleration vector is pointing in the center. I think I have the GeoGebra thing that'll allow me to visualize this. So I want to bring that up. Give me a second here to load this up. I think my 3D version does stuff like this. Yes, it does. Okay. All right. Here we go. All right. So this is the picture from last time. So let me delete this. Let me delete this stuff. We don't want that. We don't want that. And yeah, okay. So now let's go ahead and put in the I component. The I component is going to be cosine of t, but remember, GeoGebra wants x's, so cosine of t. And the j component is sine of t. And the k component is 2t. And I want t to go from, I don't know, yeah, -2, sure, or -5 to 5. How about that? We'll do that, -5 to 5. Okay. Now, as I let this draw out, right, like that, let's see what we got here. We have 3 vectors now that we're paying attention to. The red vector is the position vector. It's the original function, right? The blue vector is the velocity. Oh, and it's not drawing the thing. Oh, I have to make that fix. I did not keep that fix, evidently, from last time. Okay. All right, so I'm going to let you watch this real quick. I'm going to make a quick, oh no, I guess it is drawing it, isn't it? Oh yeah, it's drawing it. It's just underneath, so it has that. Let me change the scaling on this too. That might be better seeing here. Let's try that. Okay, something like that. Now, let's take a look at what's going on here, right? Notice that the red vector, which is r, is pointing to where you're located at. And this blue vector, velocity v, is pointing in the direction of motion. So if I was to stop time and say, at this time, which way am I flying? You would go in the direction of the velocity vector. But of course, at the next instant of time, the velocity vector is updated and changes, which means we do have a non-zero acceleration, right? And so, yeah, that ends up being those three vectors all in working together here. Now look at this one here pointing here. This is the acceleration. Now notice it is indeed, if I look above, this is looking towards the center. Oh, look at this. This looks like an ellipse. It should be circular. That's only because my scaling is off. Do you notice how this is, let me see if I can see this. Every grid marking here is 2, and every grid here is 1/2. So I just need to, let me do this. I'm going to go back to standard view. It's going to shrink everything to 1-to-1. That's probably the easiest fix. There we go. Now when I look above, look at that. Now I see that circle happening, and notice that acceleration vector. It's pointing towards the z-axis when this is in motion. So let me go ahead and animate this so we can see this in all happening here. See that? Oh, why did it stop? Oh, I know why. Because it won't show it if it goes below or above the z-axis maximum or minimum there. And that's what's happening there. So anyway, there we see what's going on there. See, we are seeing the role of r prime, and we're seeing the role of r double prime. Yeah, cool. Let's see now what else we can say. And we can now go back and calculate all sorts of other things as well. For instance, we could calculate this. What would be r prime dotted with r double prime, right? So we could calculate the dot product of r prime and r double prime. In other words, what's the dot product of the velocity vector with the acceleration vector here? And let's see what we end up getting. Remember, the dot product has everything to do with the angles between the two vectors. So this is going to give me information about the angle between the velocity and the acceleration vector for this case. So r prime dotted with r double prime, that's going to get me negative sine of t times negative cosine of t plus the j components multiplied together. So this is going to be plus cosine of t times negative sine of t plus 2 times 0. There is no k component. And remember, the dot product is a scalar. So there's no more ijk in the dot product. So I'm going to get a scalar function of t. Or do I? Well, I do, but look what happens here. I get plus sine cosine minus sine cosine. These actually cancel out, give me 0 plus 0. The dot product of the velocity and acceleration here is 0, which means they form a 90-degree angle between the two of them. So in other words, my acceleration is orthogonal to my velocity, right? So I'm going this way, but the change of velocity is saying, no, 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 no. You're going this way. Don't go that way. Go this way instead. So it's like pulls the vector, causing it to rotate. So this is a feature of circular motion. Do you see that? Circular motion. So when my when the dot product here is 0, I have orthogonal first derivative and a second derivative. That implies that I have circular motion, because what I have going on here, right, is this idea, like that. So we'll get into that more as we get into the next section. We'll get into more velocity and acceleration, but just sort of a beginning, sort of a foreshadowing, if you will. All right, last but not least here, we can calculate the cross product of these two vectors, right? So the point is, when you take a derivative of a vector, you get another vector. And so that means that you can take their cross product, you can take their dot product, and you have all of those calculations available that you ever did with any vector, right? So here we go, I, j, k. Put down r prime. Now r prime had components of negative sine t, cosine of t, 2, and r double prime had a components of negative cosine t, negative sine t, and then 0. And so we can go ahead and calculate the cross product here. All right? And remember what the cross product will do, mathematically speaking anyway. It'll give us a vector that's orthogonal to both the velocity and the acceleration. Right? So orthogonal to both of those, or normal to both of those, if you will. Yeah? So let's go ahead and calculate that. I'm going to have I, 0 minus a minus 2 sine of t, minus j. So I'm going to get sine times 0 minus a minus, so plus 2 cosine t. Then k, plus k, sine squared plus, because it's minus a minus, cosine squared. Take a look at that. And would you believe it? Look at what happens here. This is 2 sine of t I minus 2 cosine of t j. And then sine squared plus cosine squared is 1. So this ends up just simplifying to be plus k. Right? So here's what I know. This vector formed here is orthogonal to both the direction of motion and the change of that motion, right? In this case, the acceleration was pointing towards the z-axis, right? My velocity was pointing in the direction of motion, right? And so those two vectors form a plane, and this vector, this cross product vector, is going to be orthogonal to that plane, right? And that might be helpful for other position concerns, right? What we want to know that's happening orthogonal to my direction of motion and to the change of the direction of motion, right? But bottom line, I hope you see that it's pretty straightforward to calculate derivatives. We can take cross products of derivatives. We could take dot products of derivative because they're all vectors, yeah? Awesome. Now, let's take a look at another example here. We could get position functions or regular functions or vector value functions that what we are called not smooth, right? Not smooth. Now, what does smooth mean? Well, informally, it means that you don't have any sharp turns, right? No corners or no cusps, right? So something that's not smooth means it comes to like a point and it doesn't do that very nicely, right? Now, if it changed direction, continuously, that would not be sharp. But I'm talking about a curve that sort of goes up and then does an immediate like 70-degree turn and then goes off the other way like that, making a sharp point. That's where we would say that the curve is not smooth, right? So for example, of something to show you for that, take a look at this. We have r of t equaling 5 cosine t minus cosine of 5t. That's the I component, plus 5 sine t minus sine of 5t, j component, and they've limited t to be from between 0 and 2 pi. Okay? So I immediately want to go to GeoGebra and graph this. Okay, I want to see what this looks like. This has probably got a lot of shenanigans going on. Let me go ahead and get rid of the 3D version of this, and I'm going to open up the regular version, the 2D version. So we have this. I'll go ahead and put in my components here. So this is going to be 5 cosine of t minus cosine of 5t. And then the j component, I get to be 5 sine of t minus sine of 5t. Okay. And 0 to 2 pi. So I already got that down here, 0 and 2 pi. So the t values are good. I want to see this in the animation. Let's go. Okay, so we have graphed the position function. This is r pointing to where I'm at. And then there's a whole iteration through. Okay, now I'm going to turn on the first derivative. I'm going to turn on the first derivative, known as the velocity vector. I want you to sort of look at that motion for a little bit. See that? Remember, the magnitude of that first derivative tells you how fast you're going. So do you see that the particle actually stops, is at rest, right? And it's at rest. And those places where it's at rest, of course, the velocity vector, the blue vector here, shrinks to 0. It shrinks to the 0 vector. And notice that when it's not the 0 vector, it's always pointing in the direction of motion, right? Now, I'd like to now bring up your attention to these points, which I bet you could probably guess are the points where this is not sharp. Oh, sorry, where this is sharp, where it's not smooth, I'm trying to say, all right? So it definitely looks like this would be a place where the curve is not smooth. It has an instantaneous change of the first derivative. In other words, my velocity is just simply going along like this, right? And then all of a sudden, boom. See that? Right? It changes the direction like that. Notice how this came in pointing to the right. Do you see that? And then instantaneously, once it became 0, it actually instantaneously changed pointing to the left. Do you see that? Making that point not smooth. So let me now turn on the acceleration, because the acceleration, the second derivative, is going to tell me how this velocity is changing. So let's go back here, and I'm going to put this on animation and watch this for a little bit. Oh my goodness. Oh gosh. Take a look at that for a second. Try not to get dizzy. Okay. Almost think of the acceleration vector as like a string. It's like, or like a rocket engine, right, is being blasted. It's not going to make the velocity vector change right away, but it has its effect eventually. So for instance, when I stop there, notice that I'm traveling in this direction, right? How is that going to change in the very next instant? Well, it's like I'm pulling this object this way. Think of maybe that I fire an engine this strongly and it wants to go in that direction. So the very next instant, it does that. It moves ever so slightly. It can't like go from this to immediately that, right? It's got to work its way over, if you will, right? So if you think about it like, as a rocket engine, it's not going to change that immediately because it's still wanting to go in that direction. But there's a big need to change and go off to the left. See that? And so that's what that velocity vector is doing. It's like, oh, you want me to go this way to the left with this much strength? Okay. And then it updates. It's like, okay, I'm working my way there, working my way there. But of course, the acceleration is changing as well. Do you see that? And so it's always trying to pull along that velocity. Now here it goes to this place, This is almost now working in 180 degrees from each other. It wants to go this way. It wants to go down and to the left, but the acceleration says, no, 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 no. I want you to go up and to the right, right? So the effect that this is going to have is basically to slow down, to reverse course, to reverse course. And you can see this now, it's almost acting 180 degrees difference almost, right? And that's what's urging the velocity to change direction, to match up with at least being in the same direction as the acceleration as much as it can. And so these two motions are really playing together here. Do you see that? Hopefully you can visualize that a little bit better, seeing that, seeing these three vectors and their role that they play. Again, our points, position points to where you're at. Velocity points to the direction of motion that you're traveling. And the acceleration points in the direction of the change of velocity. And so it wants to turn to the left. It's pointing to there, so it's going to turn to the left. And as soon as it goes over here, now it's turning to the right. It's like, no, you got to keep going this way, right? And so it keeps doing that. I would love for you to play around with this GeoGebra a bit more and put in everything you can into here and really start to wrap your mind around how these things are visualized, how they can look. It really does a nice job of really visualizing what's going on here. Yeah. So let's now go ahead and just do some on paper calculations, right? Something like, let's just calculate the derivative, right? And see what happens. Right. So just for practice here, r prime of t is going to be the derivative of this first component. So this is 5 times cosine. So that's a constant multiple. So 5 comes out. Derivative of cosine is negative sine. Minus the cosine of stuff. The stuff is 5t. So that's going to be the derivative of cosine of stuff, which is negative sine. So negative and negative. So this is going to be plus sine of that stuff. So sine of 5t times the derivative of the inside, which is 5. And that's going to be my I component. So a little chain rule action going on there. Then, here I want to take the derivative of this again. So 5 times sine, so that's going to be 5 times cosine, minus the derivative of sine of stuff. Derivative of sine of stuff is cosine of that stuff times the derivative of stuff. And so that's my J component there. Okay? Right? So, there we have it. And if I was to look at places where this was 0, right, I would end up with places where this thing is at rest. Yeah? And so that would be places where there could be place where it's not smooth, right? Because it's gone to rest, and so it might start off in any direction after that. And so you can get cusps or nodes at those places when that happens. All right. Now, let's get into some nitty-gritty detail here a little bit. One of the most, I don't know, I'm going to nerd out on a little math fact here for you right here. We're going to see the product rule show up again, right? Now, the product rule, of course, in Calc 1 is when I take the derivative of f times g, that I get f times g prime plus g times f prime, right? So that product rule form you're very familiar with from Calc 1. Well, think about what we got here in vector math, right? In vector math, we end up having 3 different types of multiplication, don't we? We have scalar multiplication, a scalar times a vector. We have dot product, which is vector times a vector, but the dot sense, so it's a scalar result. And then r crossed with a vector, 2 vectors crossed, is a multiplication of sorts as well. So we have 3 very different types of multiplication. But what the beautiful thing is, the product rule works for each one of them, no matter the type. So there's something really deep structurally happening here, right? It's not just, oh, chance that, hey, the product rule, it works here as well. Isn't that something? There's something really structural going on about that product and how products change, right? And so let's take a look at our textbook. And I want you to take a look at these product rules that we get, different rules for taking the derivative of functions. So these are properties of the derivative, right? So we have, let R and U be differentiable vector real valued functions of t. And we get our common rules, right? So if I took a constant times a vector and wanted to take the derivative, that constant comes out and you differentiate the function itself, right? So we get the constant multiple rule straight from Calc 1. Here we have, if I take a vector valued function and I add or subtract it to another vector valued function, then take the derivative, it splits up like you think it should. It splits up term by term. And so r prime plus or minus u prime. And here's where the fun begins. Look at this first product rule. This is the derivative of a scalar function times a vector function. So this is scalar multiplication. But check out the rule. It says keep the first function the same times the derivative of r, so r prime, plus take the derivative of w, the scalar function, times r itself. That's the same exact form of the product rule in Calc 1. You could literally say this is f and g. This would be f g prime plus f prime g. Yeah? And it's the same form as the product rule. So the product rule totally works for scalar multiplication. It works for dot product. Look at this. R dot u, the derivative of that would be r dot u prime plus r prime dot with u. It's unbelievable, yeah? And then the cross product. It also works for cross product. R crossed with u prime plus r prime crossed with u. Now be very careful with the cross product. Cross product is not commutative. So it must be in this order. Don't switch the r's and the u's and the u primes around and all that. It has to be in that order because cross product changes sign if you switch it, right? So you got to make sure that it's in that order. So it's keep the first times the derivative of the second plus derivative of the first crossed with the second function, like that. And then last but not least, we have a chain rule, right? Chain rule applies to functions within other functions. And so if I take r, a vector valued function, and plug in not just t, but a function of t, it's handled in exactly the same way. What do? You take the derivative of r with the w of t plugged in, and then you have to multiply by the inside, the derivative of the inside, w prime. And so the rule for chain rule works identically, whether it's a vector valued function or a regular old scalar function. Now, let's see here. We want to then go about looking at this result. If the dot product of two vectors is constant, then we can conclude that the dot product of r and its derivative is 0. In other words, that's orthogonal. R and its derivative are orthogonal vectors if r dotted with r is a constant, okay? We're going to actually use that in a little bit here, yeah? All right, cool. Okay, I want to now prove property 7 there. So let's go ahead and see what we can do by proving that result. Okay, so we want to show that if r of t dotted with r of t is constant, some c, then r, already got its hat, dotted with r prime is 0. And so r and r prime are orthogonal in this case. Okay. So why is that true? This actually is a really easy proof, but maybe it's not easy to know what to do, right? I'm actually going to start with what we were given, right? We were given that this is true. We know that r, given, r dotted with r is some constant, okay? So since this is an equation, I can differentiate both sides with respect to the parameter, right? So I'm going to take the derivative of the left-hand side, d dt of r dot r, and that should equal the rate of change, d dt, of the constant, okay? Well, we just learned that the that the product rule is in play here, right? The derivative of a product. So I can use the product rule to write this out as keep the first function dotted with the derivative of the second function, so that's r prime, added to derivative of the first function, r prime, dotted with the second function, which is just r. And that has to equal the derivative of a constant. The derivative of a constant is 0. So we get this relationship must also be true. But this dot product, no matter what it is, right, r dot r prime, is the same as r prime dot r. And so I end up getting 2 times r dot r prime is 0. Remember, dot product is commutative. And so I can rewrite this the other way. Whatever value this is a copy of it. But wait a minute. 2 times this number is 0. So that means the inside thing must be 0, which tells me the conclusion that r dotted with r prime is 0. And so that tells me that in this case, when I dot a vector valued function with itself and I get a constant function, something that doesn't rely on the parameter t, I get a constant function like that, then I know or can conclude that the two vectors, the vector and its derivative, are orthogonal, right? We're going to use that result in the next section. So I wanted to prove it and show it to you happening there. Okay, awesome. Let's see here. So okay, yeah, so practice your differentiation and all of that good stuff. Now let's talk a little bit about integration. All right, so again, the rule's very simple. How do you integrate a vector valued function? You integrate component wise. And so it's just like a 2-for-1 deal or a 3-for-1 deal, right? And so let's just take a look at our first example. Let's dive right in. So suppose I ask you to take the integral of ti plus 3j with respect to t, right, with respect to the variable. Now this is an antiderivative, it's an indefinite integral. So this is an indefinite integral, which means I should get an infinite number of answers, right? I'm going to get a plus c, but of course the plus c this time is not just a constant, it's a constant vector, right? So that plus c will have an I component and a j component, right, as well. But this is actually very straightforward. All I have to do here is integrate the t, which is going to be t squared over 2, right? Now I'm going to get a plus c here, right? So in fact, let me write it out this way. This is the first and last time I'm going to do it this way, right? Would you agree that I would get a plus c from this first integration, yeah, like that? And that would be the I component. Yeah? Then I would integrate the 3 to get 3t, and it would get its own c, maybe call it c2, and that's the j component. Do you see that? Now, what I can do at the end of this then is say that, well, the I can distribute, so I get 1/2 t squared I plus 3tj, and then I have this plus c1I plus c2j. Do you see that? And so instead of writing the c1 and the c2 individually, here's what I'm going to do. I'm just going to collapse this arbitrary c1, c2 vector and call it just some big capital C vector like that. So when I go ahead and do this problem again, I'm just going to say that this is t squared over 2i plus 3tj plus a big vector c. That's it. Okay, that's all I would have to do for that. Yeah. So integrate component-wise. So the only difficulty here is going to be remembering how to integrate. That's it. Because it's certainly nothing new that's added in difficulty with vector valued functions here, right? Let's go ahead and do another example. This time let's do a definite integral. And so I'm going to integrate from some t value to some other t value. So let's calculate the integral from t equals 0 to 1 of r of t dt. And here I'm going to give you that r is this. So this is the integral from 0 to 1 of the cube root of t I plus 1 over t plus 1 j plus e to the negative t k, and all of that dt. Okay? So I want to integrate this vector. It has an I component, j component, k component, and I want to integrate each one from 0 to 1. And so I just do that. So I'm going to apply the fundamental theorem of calculus in all three components, right? So I first get an antiderivative of this. This is t to the 1/3. So t to the 1/3 would be add to the power 1, so 4/3, divide by new power. But I don't divide by 4/3, I'll just multiply by 3/4. So I already do that right there. So I don't have a fraction divided by a fraction, yeah? Okay, and I want to evaluate that from 0 to 1. And whatever I get there, that's the I component. Yeah. Let's see, what do we have here? This is going to be a u sub. Let's let u equal t plus 1, right? Then du equals dt. So nothing comes out nothing special comes out of the substitution. This is like integrating 1 over u, which is the natural log of the absolute value of u. And so this ends up being plus natural log, the absolute value of u, which is t plus 1, evaluated from 0 to 1. And that's my j component. Then integrating e to the negative t, that's also a u sub. Let u equal negative t. Then du equals negative dt. So a negative comes out in front. And I'm integrating e to the u, which is e to the negative t, and evaluate that from 0 to 1. Right? And that's the k component. Okay, so like I said, these are not bad. They're just 3 integration problems in one, yeah? Which I guess they could be bad if the integrations are terrible. But these haven't been too bad so far, but you know. So anyway, so now plug in the 1 minus plug in the 0. So plugging in the 1 gets me 3/4. Plugging in 0 gets me 0, so minus 0. So that's it for the I component. It's 3/4. Plug in 1 here, I get ln of 2 minus plug in 0, so minus ln of 1. Ln of 1 is 0, so this is going to just be plus ln of 2. Absolute value sign's not needed because 2 is a positive number. So j there. Then minus whatever I get here. So plug in 1, so I get e to the negative 1 minus a minus e to the 0 k. Let me just clean this up, and then that'll be my final answer. So this is going to be 3/4 I plus ln of 2 j minus e to the 0 is 1. And then this is e to the negative 1. So that's 1 over e. So let's see here. Oh, I think I made a sign mistake. Yes, I did. I made a sign mistake. Please catch this. I plug in the 1. I get e to the negative 1. But then it's minus e to the 0, right? And so, yeah, I get a minus sign there, right? Now, here's what I can do, right? I could push that negative sign through here to swap it. And so what I can say here now is plus e to the 0, which is 1, minus 1 over e. Okay. Imagine that, right? After all that, it's not the calculus, it's just the pesky algebra mistake. It's the sign mistake that gets you. Yikes. All right, look that over. Make sure that you're okay with that sign change like that. And I mean, that's the story with integration. It really is just term by term, right? Now, there's a type of problem that I want to finish this video on, and that is trying to find the original function if you're given the derivative. Okay, so let's take a look at that type of problem. So let's say we're given r prime of t, right? And we're given that that is cosine of 2t I minus 2 sine of t j plus 1 over 1 plus t squared k. All right, so we're given that that's the derivative of some r. I don't know what that r value is, right? I don't know what that r function is, but this is its derivative, okay? And we're also told another piece of information. We know also, we know somehow that r of 0, when I plug 0 into r, whatever r looks like, it's 3i minus 2j plus k. We call this an initial condition. So people who are in differential equations right now just perked up their ears, right? Because this is the derivative of an unknown function, right? And I want to find that unknown function, r, but I have a certain initial condition. I know r at 0, but I don't know r anywhere else. But I can figure that out because I know that this is the derivative of r. So here's how we can proceed. All right? So my first shot at this is knowing that we know r would have to be the integral, the antiderivative of r prime of t dt, right? And so I want to take the antiderivative of each component, right? And that'll at least get me started. And then I'll have a plus c, right? An infinite number of choices here, if you will, yeah? Well, I'm going to then use this condition to figure out what that plus c has to be. But I'm getting ahead of myself. So let's finish this off. I'm going to take the integral of each component. The integral of cosine of 2t, that's going to be a u sub. Let u equal 2t. Then du is 2 dt, so a half comes out. So I'm going to get 1/2. The integral of cosine of u is sine of u. So sine of u, which is 2t, right? And I'm going to get an unknown constant, right? So, but let's just do I. Let's just do that for now. Okay. Now we anti-differentiate the second thing here. So this is going to be a straightforward -2. Integral of sine is minus cosine. So that's going to minus the minus to get 2 cosine of t. That's the j component. And then 1 over 1 plus t squared. Now don't freak out on this. This is just a memorized fact. You might recognize this as arctan. Arctan. So this is just simply arctan of t. And that's the k component. And then, of course, plus c, right? That is the antiderivative of r prime. So this is what the form of r has to look like. The only thing now is that the I component has to have this, the j component has this, the k component has this, but each one of those components might be shifted differently. There might be a constant part of that to make the r work out. So now the second part of this problem is I'm going to plug 0 into what I calculated, right? And I know what I was given, this mess would then have to equal that. And so whatever doesn't match up, the c has to take care of to make those two things match, right? So here's what I'm going to do. Now plug in t equals 0 into the thing I just calculated. So I'm going to get sine of 0, which is 0. So I get 0i plus plugging 0 into cosine gets me 1. So 2 times 1, so plus 2j. Arctan of 0. Arctan of 0 is what angle gives you a tangent that's 0, and that would be 0. So that's 0k. And then plus c, right? That's what happens when I plug in t equals 0. I get this vector. But I also know, by the given information, I should get this vector. This has to equal 3i minus 2j plus k. So c has to make it work. Do you see that? So, of course, 0i is gone, 0k is gone, and I have 2j over here. So let's subtract 2j from both sides, get that out of there. And that, algebraically, tells me what c has to be. So c has to be 3i minus 4j plus k. See that? That is the plus c that makes this work and this condition work, right? The antiderivative made this requirement work, and this condition made this c, this value for c makes that work. Yeah. So now, what's my final answer? Let me write it all together here. So what's my function? R of t equals, let's go for the I component. The I component is 1/2 sine of 2t plus the 3. That's the I component. Then, what's the j component? Well, plus 2 cosine of t minus 4. That's the j component there. And then the k component, I get plus arctan t plus 1. And that's the k component. And the c was already sort of built in, right? So there we have it. This is our function r of t, whose derivative would be this. And when I plug in 0, I get this. Yeah. And so mathematically, I was able to figure that out. That's a type of problem that we will see in the next section as well, because as you might imagine, the way we're going to use this integration of vector is I'm going to throw at you an acceleration vector, right? And how do I figure out the velocity from an acceleration vector? Well, I have to integrate it, right? And so I'm going to have an acceleration vector, and I'm going to need to take the antiderivative to get the velocity. And then from that, I can get the position, right? And this literally is the way that we can get how orbits work in space. Not 3D space, but space, outer space, if you will, right? Because we have laws, Newton's laws, talk about how accelerations work and forces they work, right? So force equals mass times acceleration, right? So we know how accelerations work much more readily than positions, right? And so understanding the accelerations of planets, understanding the accelerations due to gravity, understanding those sorts of forces and accelerations is the starting place. Once we understand that, we can integrate to get velocities. Now we know how fast a planet's traveling, right? Or something that's orbiting is traveling, yeah? Then, once we know velocities, we know position, right? Because we can integrate and come back to that. We're going to actually talk about that next time. In 12.3, we're going to start talking about velocities and accelerations going backwards and forwards, and really getting into some cool stuff about how stuff flies around, right? And this can, like I said, this can work for orbital mechanics, how things orbit. It could be like space flight controls, sorts of mathematics problems like that. And so good stuff. This is foundational stuff for lots of things that get programmed into control systems and such. Yeah. Awesome stuff. So with that being said, looking forward to checking in with you next time, which will be on Thursday. And so looking forward to that. Hope you're staying well. Hope you're staying happy as much as you can. And looking forward to checking in next time. And until then, everyone, be well. See you later.